Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, physics perspective. This is lecture number 42 and we will be discussing RLC FinFET modeling, right. In our previous lectures, we have actually gone through the FinFET structure, how to extract high frequency capacitances and resistances, what is the meaning of de-embedding. We have also looked into the Y parameter modeling and then various figures of merits for high frequency such as uh, transition frequency and maximum frequency of operation. What we will be looking into is we will look into the basic idea about a FinFET and how can FinFETs be used for circuit analysis, right. So, that brief idea I will be able to give through this lecture series. So, we will be looking into RLC FinFET modeling. So, if you look at the structure here, this is another configuration of FinFET, and if you see this slide, the second schematic here, this is sort of a two fin structure, right, and you can have two gate structure. So, you see this is gate number 1 here, this is gate number 1 and this is sort of gate number 2, let me say. Then this is also referred to as interdigitated structure, right, and the drain is common between this and this. So, you have a source here, you also have a source at this end, and therefore, typically you have 4 such devices inbuilt within them, where the drain is being shared between all the 4 elements, and you have got structure here and here. As you can see, this is basically a TEM image here, and this is the gate. So, this gate which you see is surrounding the fin or surrounding the this thing in all the directions, and this is the gate which you are giving, a metal gate. Now, if you take this and do a layout for that one, then you see on the left hand side is basically the layout for this one, and this provides to you the interdigitated. So, you have this fins which are running across the board here, right, and then you have the gate which is the black colored gate here. So, it is 1, 2, 3, 4, 5, 6 fin structure which you see here, and then there are 6 fin structures here. So, effectively there are 12 fins which actually take care of the various structure. Whereas at the bottom side, as you see, you have a planar MOS device which we have already studied quite along. Here what we are doing is we are adding a third dimension or a third sort of structure which adds to the total current and much better handling of the current. We define two terminology already defined with you, but let me reaffirm. One is known as a fin pitch, right, and it is basically, so if you have one fin here, let us suppose, and you have another fin here, let us suppose, then the fin pitch is basically referred to as the distance between center to center. So, if this is this, then this is known as fin pitch, right, fin pitch. This is between the center of one fin to the center of another fin, and it is given by the sum of S fin, which is this one, this is S fin, right, and so this is basically, if you look carefully, this is W by 2 here, and this is again W by 2. So, that is the reason when you add 2 W by 2 you get W, right, and that W is added with S fin here. So, W plus S fin gives you P fin. So, the fin pitch is given by the width as well as this distance is W, right. So, if you want to have a better integration of the device or the integration density, you want the integration density to be very high, it is always advisable to make your S fin as small as possible, right, and once you make the S fin as small as possible, you end up having therefore larger number of fins within the same area. So, your area goes on reducing, but your power handling capacity becomes larger. However, the cost you pay for it is of course the capacitive element also goes on increasing. Now, if you look at this structure here, this is another structure which is available and you can have a look into it, that it is given in this research paper here, and it is given by the structure which you see here. It is again a raised source drain structure. So, you see you have source drain on this side, right, source drain city side. You have the gate, green colored is the gate which is the metal gate. The T gate and T oxide, you can see T gate is the thickness of the gate here, Tox, the yellow colored one, is basically the oxide thickness for the top gate, and T oxide side is the for the side one. So, it is something like this. You have a tunnel here, and this is my yellow colored one. So, this happens to be my Tox here on the top, and this is Tox at the side. It might be true that the Tox top might be equal or might not be equal to T sideways. This is the width of the fin, which you see, which we have already discussed. This is the H fin of the fin, because you will have another one block available here, there will be another block available here. So, we define this to be as S fin by 2, half of the S fin which you see. This is basically a cross sectional area which you see, and several analytical models are used to evaluate the geometry dependent parasitics, which I have already discussed with you in our previous slides. Now, let me show to you what are the geometry parameters used by this paper. At least they have used a gate length of 14 nanometer, width of the fin to be approximately 7 nanometer, the thickness of the gate material, which is this one, right, is 14 nanometer, top layer oxide layer, which is this one, is 1.4, and the oxide side is 1.1, which means that this and this are exactly equal, they have used, which means that the gate has equal control over the channel on all the 3 sides. So, when you keep your oxide layer constant, you end up having the same sort of addition or same sort of control over the channel from all the 3 sides. Now, let me now come to the next slide and show you the parasitic capacitances which are available in a FinFET, right. So, there are 4 basic parasitic capacitances, and there are 5 basic resistance elements which are available with us. And the parasitic capacitances are inner fringing field capacitance known as CIF, overlap capacitance, outer fringing field capacitance, and AP to gate capacitance. We will go one by one and show you how it is done. So, what we have done is we have to explain to you. So, we have cut this one by this axis, right. So, we have cut in this plane, right. So, this is, let me assume this to be as a, we can also cut it. So, this is AA plane, you see, this is A and this is A bar. Now, if you look at this structure here, this is the AA plane and this is the BB plane, right. So, let me see which one is the AA plane. This is the AA plane here and this is the BB plane here. So, if you cut it across this dimension, we say define this to be as a BB plane, and this is AA plane or AA bar plane, whatever you want to name it, in a transverse cut if you do, right. And if you now go back to this slide and if you take a photograph from the sideways, then we define CIF as the inner fringing field. I will explain to you, this is source or maybe this is drain, this is the gate layer, this is the oxide layer, this is the channel layer which you see. So, inner fringing field is basically between the oxide layer or the AP layer and the channel here. This is the channel here. Similarly, CIF also can be written as this. This is CIF between the gate and the N plus layer and the N plus layer. Why inner fringing field? Because it is inside the device itself, right. Then you also have an overlap capacitances. Why? Because the gate overlaps with source and drain, and because of which these red colored are basically your overlap capacitances, right. And these basically overlap capacitances add to the total capacitances of the network. Then you will have also the outer fringing field capacitance given by these blue ones, right. This is the C overlap, this is the blue one, will give you the C overlap capacitances. Overlap capacitance and the outer fringe capacitance. Outer fringe is not through the device, but outside of the device. Then you have AP to gate capacitance. What is AP to gate? Let me rub this portion for you. So, AP to gate is what is shown here. So, this is your AP to gate. So, this is your gate and this is your AP layer which you see, and the red colored is basically my AP to gate. So, these are the 4 basic parasitic components, and there are 5 resistive components referred to as a spread resistance from channel to source drain extension, referred to as RSP1, then the sheet resistance of source drain extension under the spacer, then spread resistance from source drain region to the SEG, and there are contact resistances of A and contact resistance of the bottom surface. So, top surface and bottom surface. I will explain each one of them individually to give you an idea about what these values are. So, if you look at contact A and contact B, it is nothing but the resistance at this particular point, right, at this and this. So, why? Because from the source and drain you are trying to take contact, right. from the front gate as well as from the back gate. So, all those will contribute to your contact resistances, right. Then you also have this sheet resistances occurring. You see, this is the sheet resistances which is occurring because of the channel region which is not under the gate, it is in the spacer area. That also contributes to the total resistances in the region, and that is the region I have shown here as the sheet resistance, this one, right. Then of course, the spread resistance from the channel to source drain extension region, and finally the spread resistance from the source drain to the SEG layer, right. So, there are 5 resistances which act to the body, and these are actually not only structurally dependent, they also depend upon the doping concentration and also on the bias conditions. There are 2 important sort of figure of merits which any RF designer looks into. Is one is the current gain cutoff frequency and also the maximum oscillation frequency. And I am not going to details of how I am deriving it, but you can see it in this research paper here, but these are derived by these quantities which is given by this formula here and by this formula here. As you can see, it is directly depending on the value of GM, and that is expected also. So, the current gain cutoff frequency, if you look, depends on the transconductance. Higher the value of transconductance, more will be the FT value, which will have larger value, which means that if you have larger number of fins, you typically therefore have larger transconductance available with you. But this larger transconductance will also make this CGDS and CGD also will go on increasing when your fin becomes either increase in height, or because of the non-planarity of the structure, the capacitance value will become larger and larger. Now, to obtain the intrinsic characteristics including both GM and GDS, right, then we need to perform a calibrated 3D TCAD, and many people have, or many researchers have actually done this 3D calibration. Our group has also done it, and there have been quite a substantive result in saying that after you do a proper calibration, you are able to extract these values of resistance and capacitance, fit in this model and try to extract the value of FT as well as F max, which is there on the right hand side. Okay. So, these are the 2 figure of merits which are important and should be taken care of. Now, achieving both a high height of the fin and a small S fin, obviously there will be a problem in process integration, because high H fin effectively means that the fin height should be high, but then this is limited by the process which you are doing it. Similarly, a small S fin will be determined by the lithographic step which is there, right, and therefore there are many techniques. For example, tilted ion implantation, a methodology is there by which you can actually do such type of small S fin and high H fin design. If you want to increase S fin, which is the fin distance between 2 fins for a fixed H fin, what happens is that the parasitic capacitances with respect W effective increases, and the reason is both outer fringing field and the epilayer component are increased. Why? Because when you make the S fin larger and larger, you end up having more and more fringing field available to you, outer fringing field, and because the gate and source drain region get overlapped to a larger extent, and therefore there is a sudden increase in the value of capacitance. So, if you look at the right hand side figure here on this part, then I am plotting C para by W effective. As you can see, when S fin by H fin actually goes on reducing, the effective value of the C para by W fin goes on reducing, which effectively means that, so when S fin is equals to H fin, which means the ratio is exactly equals to 1, you will see that the minimum value goes down very low, right, it goes down to a very low value, the minimum point, and the minimum point not only goes down, but it also shifts to the right. Right means to the fin height, means I am able to achieve a lower value of C para by W effective at a relatively larger fin height. I can extend my fin height to a larger extent. So, what has happened is, here the fin height was small, and as you make the fin height larger and larger, this quantity starts to fall down. At this particular point, S fin is equals to H fin, and for that this is the fin height for which you get, or almost this region is the fin height where you get the minimum value of the C para by W effective. Now, a large, obviously we have discussed this point earlier also, that a large S-fin to H-fin ratio is beneficial. A large H-fin to beneficial to reduce the total source drain resistance as well as W effective. Now, therefore for a given S-fin to H-fin ratio that have also increasing the height of the fin or the fin pitch, distance between the two fin, increases the RSD value and W effective. Now, therefore, when you use this device for RF or analog applications, the idea or the objective or the function which you need to improve upon is FT and Fmax, right, and that will improve the better value, and therefore it is very critical to fix the value of S-fin by H-fin. The same thing can be seen at the bottom side. This is basically RSD into W effective, and as you can see, the reverse is true here, of course. Why? Because as you make your S-fin by H-fins go more symmetrical, which means that S-fin is almost equals to H-fin, and as the value of S-fin by H-fin, by decreasing the height of H-fin, what you are effectively doing is you are reducing the resistance, source drain resistance, right, and as a result this value is going down and down, right, and that is the reason you can see the second half of the graph in that manner. Therefore, to conclude all these things, a smaller S-fin to H-fin ratio is preferable for improving both FT and Fmax, right. So, when you want to design a very small or a very low dimension FinFET for RF and analog application, we should actually focus on the parasitic capacitances rather than on absolute value of resistances. So, resistances do not come down or go down very heavily, whereas parasitic capacitances go down very fast. Now, that can be seen from your graph seen on the left hand side, where the fin number is given here and you can plot FT and Fmax with various values of fin height. Exactly the same observation which we saw in our previous discussion, right, and we can actually say that a reduced S-fin by H-fin will be a preferable solution. So, what we do is that if you look carefully here, we are plotting fin height and we are doing a fin spacing. So, this is S-fin on this side and we have H-fin on this side, right, and we are saying that there are actually 4 regions of operation where you can actually look into the value of the various parameters. And as the operation of frequency goes on increasing, you see the graph actually shifts to the bottom, right. Not only it shifts to the bottom, but it tends to become more and more divergent for a large value of fin height for the same value of fin spacing. And therefore, typically what we see is if you look at region number 3 and region number 1, region number 1 is the one where typically you require S-fin to be approximately equals to W-fin, and you do not operate below this. This is sort of a lowest most critical design parameter. You do not operate your device below S-fin equals to approximately equals to W-fin, because then what will happen is that the fin spacing will go relatively down and it will be beyond the process integration. It will be very difficult to do a process integration. Now, as you can see, this is from 260 gigahertz to about 360 gigahertz. We have plotting the fin spacing. As you can see, as the fin height goes on increasing, your fin spacing also has to increase in order to sustain a reliable output performance, right. And therefore, there is a maximum S-fin to H-fin ratio, which is basically in region 3, this one here, that if you take a non-planar or you take a non-planar FinFET, then its layout area should be comparable to that of that or less than the planar FETs. If you look at region 3 here, then if I, for example, if I fix my fin height to be 10, then for 260 gigahertz of operation, I need to operate my S-fin to approximately equals to 35 to 40 nanometers of S-fin, correct. So, if I therefore see the variations of S-fin to H-fin, so if I do S-fin to H-fin here, you will see this to be equals to 4, here approximately, right, and this is the point where it is approximately equals to 2. You see 20 and then you have 40 here, right, you have 30 and then you have approximately 60 here. So, this is the point where S fin by H fin is approximately equals to 2. Anything to the left of it is a preferred one for non-planar structure, whereas if you go to the right, this graph gives you S fin by H fin approximately equals to 1, which means they are exactly the same. And if you look at this particular point, it tells you H fin is approximately 6 times the width of the fin. So, what we have done by discussing these things is that it is always advisable to keep your region of operation in somewhere around region 3 in order to operate it as a good device, right. But however, if you want to operate for a higher frequency, advisable to come to region 4 for that matter, right. And therefore, if you want to operate at lower frequency, region 3, make your fin height smaller. Want to operate for a higher frequency, go for a higher fin, but reduce your fin spacing, and that will give you a better design problem. As I discussed with you already, I am reiterating the fact that a small S fin to H fin ratio is a sort of a preferred design. Both FT and Fmax, as I discussed with you, are influenced by the parasitic capacitances than by source drain resistances. Now, let me come to the last part of this talk, where we try to give you an option that we had two types of FinFETs, if you remember, an independent gate and shorted gate structure, and you can use them for all practical purposes. For example, you can use them as a simple inverter here, you can use them as a simple inverter here, and these are the various forms of inverter you can see. And what we are doing is that if you just compare the inverter here, then for low power and independent gate and independent IGN and IGP, PMOS being independent, NMOS being independent, we see that if you are normalizing with respect to SG, the maximum TP which you get is 3.67. TP is basically my latency which you get. It is much larger in case of low power, and expected also, because your current is small, current carrying capability is small, your TP will be large. Now, this, if you look carefully here, this is basically a single gate inverter here, this is also an inverter here, and I am assuming that the substrate potential has been given. So, the substrate bias effect is there. Here there is no substrate bias because you have shorted to the output here, right, shorted the output and input here. Similarly, if you do a comparison of NAND 2 gates, and if you assume that your shorted gate is the most standard one, then you see that the other ones are relatively larger in dimensions. Schematic of NAND 2 gates. So, if I want to use a NAND 2 gate by using FinFETs, then this is, so these are the two PMOSs pull up which is there, and there are two NMOSs which are here. So, this is NMOS number 1 and this is NMOS number 2, this is PMOS 1, let us suppose PMOS 2, and this gives you a, so gives you a pull up ratio. I am trying to take out the output here, I can take it from anywhere I want. So, this is my output here, and giving A and B are two inputs which are available here. So, this is one form of NAND 2 gate, and this one is basically for the shorted gate, and this is for low power design, and this is for empty gate, right. And you can see here that these two PMOSs, what we have done is that, why low power, because in the substrate we have been trying to give potential such that the threshold voltage goes down and you can actually have a low power design. So, you can see here both my substrates here and here have been given an extra power, right. So, you are actually giving a VBS, bulk to source potential, which will lower the threshold voltage and have a lower power, right. Same thing happens on the right hand side for the empty design. Now, if you do a NAND gate here, then this is for the XT gate, extended gate which you see, right. Now, this is an asymmetric gate FinFET structure, where the symmetricity is not maintained across both using inverter, NAND 2 gate and NAND 2 S gate, shorted gate. So, this is the NAND 2 shorted gate, this is NAND 2 ordinary gate, and this is what you see. So, you see this is basically the shorted gate structure where blackened is there. This is not a shorted gate structure here. So, within the pull down structure you have one which is not shorted, which is one is shorted. right. And and these are the various techniques by which you can use FinFETs for logical gate operations, right. Now let us look at the leakage delay spectrum of various logic gates. On the y axis you have the average FO4 delay, and on the x axis you have the average I of. I of is basically the leakage current which you get. I of means when your gate voltage is lower than the threshold voltage, you have subthreshold leakage, direct tunnel leakage, and so on and so forth. Now if you look at the points, quite interestingly, I would want my I of to be low, and I also want my average FO4 delay to be low. So within this graph, the points located in this region, right, the points will be the most preferred one, where the average I of is also relatively low, and your average FO4 delays are also very low. And one thing which comes into your mind is basically your asymmetric gate inverter using FinFETs. They typically have an average FO4 delay which is relatively small, and of approximately 5.3 to 5.4 picosecond, and typically the average I of currents are much smaller, approximately 10 to the power minus 12 amperes of current. So around 10 pico ampere current is there. So you can see that preferred are this one. However, if you move right to the right hand side, you see your I of is large for a shorted gate inverter, right. However, its average FO4 delay is very large. So if you can afford to have slightly less low power device but high speed device, then advisable to have a single gate inverter where you use these FinFETs for modeling purposes. Similarly, if you look at the top side, you will have NAND 2 gate here in this case, right, NAND 2 gate here. So these are the few leakage delay spectrums of various gates which you see. Now we will end up by giving you a FinFET example in latch. So if you see at the left hand side, it is basically a D latch, and this is basically my transmission gate here. So when my clock is high and clock bar is low, my TG is on, right, transmission gate is on when my clock is high and my clock bar is low, because clock bar drives my PMOS and clock drives my NMOS. When it is low, then any D appears as D bar here and is fed at this particular point, and this D bar appears as D here, and therefore this D appears as D here, which means that whenever your clock goes high and clock bar goes low, this becomes transparent and you are able to transmit D to Q, right. That is what you can do it. You can use these TGs from FinFETs as well as these cross coupled inverters here using FinFET, shorted gate FinFET. On the right hand side, it is again the same concept here, that if you give a D here, it will appear at Q when the clock equals to 1. When the clock equals to 1, this switches on and you force this D to reach here, and as a result this will appear as D bar at this particular point. Similarly, D bar will appear at this particular point, correct. So these are sort of the right one is known as a half swing design and the left one is known as a transmission gate design, right, and these are the designs which are used in FinFETs. Some of the other FinFET flip flops are shown here on the left hand side, TG based, and this is basically half swing based. This TG based is again, so what you do is that in the first clock, when clock is high and clock bar is low, you let this D fall onto this particular value, but by that time this is off state and therefore it is non transparent. When clock goes to low and clock bar goes to high, then this becomes on and therefore this transmits to Q here, right. So it happens in 2 clock cycles in a sense, and it D therefore appears at Q, right. So this is an example of a transmission gate design. This is the last one, which is basically a 6T FinFET based design, 6 transistor FinFET SRAM, where this is the access transistor here, this is the access transistor, and this is the 2 latches which we see. So you can do like this and this and this, right. So we have access WL here, word line, and you have bit line and you have bit line bar here, and therefore you see this is the bit line bar which is running here, you have bit line which is running here. When WL goes high, your latch becomes transparent to bit line and bit line bar, and you will be able to therefore read and write within the cell. Now if you look at the comparison of the FinFET SRAM cell, there are many comparisons here. You can refer to this research paper, and you can get large amount of information from this research paper which has been written by the authors here. So, let me recapitulate what we did till now. We looked into a FinFET based circuit design, FinFET based circuit design, and we saw that how we can use optimally the various types of FinFETs in order to get the best result available to us. We also saw that if you plot FO4 delay with respect to the number of the I of with respect to I of, where should our device be stationed for the best performance and how it can be changed. Finally, we looked into the various architectures of if not various, maybe one architecture, which is transmission gate based latches, flip flops, inverters, 2 input NAND gates, and you can also extend this work to a 2 input NOR gate, right. So, the way to move forward and understanding FinFET is draw its equivalent circuit model, find the best performance, use that best performance model for all your circuit application procedures. With this, let me finish this part of the lecture. Thank you for your patient hearing.